The universe in a grain of sand, heat and thermodynamics in our world. Have you ever wondered how a simple cup of coffee stays warm? Or why ice melts on a hot day? The answers lie in the fascinating world of heat and thermodynamics. These fundamental concepts govern everything around us, from the smallest atoms to the largest stars. Thermodynamics is like the cosmic accountant, keeping track of energy transactions in the universe. It explains how energy flows and transforms, shaping the world we experience. Understanding heat and thermodynamics unlocks secrets about the very fabric of reality. Think about engines that power our cars or refrigerators that keep our food cold. These everyday inventions rely on the principles of thermodynamics. By grasping these principles, we gain a deeper understanding of how these technologies work. So let's embark on a journey into the enthralling realm of heat and thermodynamics. Together we'll uncover the fundamental laws that govern energy and its transformations. Feeling the heat. What exactly is heat? We feel heat's effects all the time. A warm summer day, a hot stove, a cozy fireplace, all involve heat. But what exactly is heat? Heat is simply energy in transit. It's the transfer of thermal energy between objects or systems at different temperatures. When you touch a hot object, energy flows from the object to your hand and you feel it as heat. This transfer of energy occurs because of the difference in temperature. Heat always flows from a hotter object to a colder one, trying to equalize the temperatures. Think of it like two water tanks connected by a pipe. Water flows from the tank with higher water level to the one with lower level until they balance out. Heat does the same, flowing from higher to lower temperature until thermal equilibrium is reached. From ice to steam, the dance of temperature. Temperature is often confused with heat, but they are distinct concepts. Temperature measures the average kinetic energy of the particles within a substance. In simpler terms, it tells us how hot or cold something is. Imagine a group of people dancing. Temperature is like the average energy of their movements. A high temperature means they are moving rapidly, while a low temperature means they are moving slowly. Temperature scales like Celsius and Fahrenheit provide a numerical way to express how hot or cold something is. These scales are based on fixed points, such as the freezing and boiling points of water. Understanding temperature is crucial for comprehending how heat flows and how systems reach thermal equilibrium. Energy within, unmasking internal energy. Now let's delve into the concept of internal energy. Every object possesses internal energy, which is the sum of the kinetic and potential energies of all its particles. Think of a pot of water on a stove. The water molecules are constantly moving and vibrating. That's their kinetic energy. They also experience forces between them. That's their potential energy. Internal energy is directly related to temperature. As temperature increases, the internal energy of the object also increases. This is because the particles move faster and have greater kinetic energy. Internal energy is a fundamental concept in thermodynamics, as it helps us understand how energy is stored and transferred within systems. Section 5. Zeroing in on thermal equilibrium, the Zeroth Law. The Zeroth Law of Thermodynamics might seem obvious, but it's the foundation upon which we build our understanding of heat flow. It states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Imagine three objects, A, B, and C. If A and B are both in thermal equilibrium with C, meaning no heat flows between them, then A and B are also in thermal equilibrium with each other. This law allows us to use thermometers to measure temperature. When a thermometer reaches thermal equilibrium with an object, we know it's also in thermal equilibrium with any other object at the same temperature. The Zeroth Law might seem straightforward, but it establishes the concept of temperature as a measurable property and forms the basis for all temperature measurements. Section 6. Energy's Grand Balancing Act, the First Law of Thermodynamics. The First Law of Thermodynamics, also known as the Law of Conservation of Energy, is a fundamental principle in physics. It states that energy cannot be created or destroyed, only transferred or transformed from one form to another. Think of it like a bank account. You can deposit money, withdraw it, or transfer it between accounts, but the total amount of money remains constant. In thermodynamics, the account is the system's internal energy. Heat flowing into a system increases its internal energy, while work done by the system decreases it. However, the total energy of the system and its surroundings remains constant. This law has profound implications, telling us that the total energy of the universe is constant and will always remain so. It's a powerful concept that governs all energy transformations, from the smallest atomic interactions to the largest cosmic events. Section 7, One-Way Street for heat implications of the First Law. The First Law of Thermodynamics has important implications for how we understand heat flow and energy conversions. For example, it tells us that we can't create a perpetual motion machine, which is a hypothetical device that operates indefinitely without any external energy source. Such a machine would violate the First Law because it would be creating energy out of nothing. The First Law also explains why heat engines, like those in cars, can't be perfectly efficient. Some energy is always lost as heat to the surroundings, limiting the amount of work that can be extracted from the engine. Understanding the First Law is crucial for analyzing and designing thermodynamic systems, from power plants to refrigerators, as it governs how energy is used and transformed in these systems. Section 8, Disorder's Inevitable March, introducing entropy and the Second Law. The Second Law of Thermodynamics introduces the concept of entropy, which is a measure of disorder or randomness in a system. The Second Law states that the total entropy of a closed system always increases over time. Imagine a deck of cards arranged in perfect order. If you shuffle the cards, the order is lost and entropy increases. The same principle applies to thermodynamic systems. Natural processes tend to move towards a state of greater disorder. For example, heat flows from hot to cold, spreading out the energy and increasing entropy. The Second Law has profound implications for the directionality of natural processes and the concept of time's arrow. Section 9, the arrow of time. Why the Second Law matters. The Second Law of Thermodynamics helps explain why time seems to flow in one direction. As entropy increases, the universe becomes more disordered, and it's highly unlikely for it to spontaneously return to a more ordered state. This is like dropping a glass of water and watching it shatter. It's highly improbable for the shattered pieces to spontaneously reassemble and the water to jump back into the glass. The Second Law also has implications for the efficiency of energy conversions. Since some energy is always lost as heat, which increases entropy, no process can be perfectly efficient in converting one form of energy to another. The Second Law is a fundamental principle that governs the direction of natural processes and the limits of energy transformations. Section 10. Thermodynamics in action, from refrigerators to stars. The principles of thermodynamics are at play all around us, from the simplest everyday objects to the most complex natural phenomena. Refrigerators, for example, use refrigerants to transfer heat from the cold interior to the warmer exterior, keeping our food cold. This process requires work, which is why refrigerators need electricity to operate. Power plants use heat to generate electricity. They burn fossil fuels or use nuclear reactions to produce steam, which drives turbines that power generators. Stars, the engines of the cosmos, are powered by nuclear fusion reactions in their cores. These reactions release tremendous amounts of energy, which is radiated out into space as heat and light. Understanding thermodynamics helps us appreciate the workings of these systems and countless others. Section 11, Conquering G-Mains, Heat and Thermodynamics in Your Hands. As you prepare for the G-Mains exam, mastering the concepts of heat and thermodynamics is essential for success. These concepts form the foundation for many questions in the physics section. Focus on understanding the fundamental laws of thermodynamics, their implications, and how they apply to various scenarios. Practice solving numerical problems involving heat transfer, work, internal energy, and entropy. Visualize the concepts, use analogies, and relate them to real-world examples to solidify your understanding. Don't hesitate to seek clarification from your teachers or peers if you encounter any difficulties. With dedication and a clear understanding of heat and thermodynamics, you'll be well equipped to tackle the G-Mains exam with confidence.